is multi-body. We're also going to cover something called Hooke's Law, but that's, there's no E in Hooke. But that's actually not going to be covered in any great detail today, or this term. I want you to have exposure to what Hooke's Law is. I have a good Hooke's Law lab that we're going to do, but Hooke's Law is just the force you get from springs. It's a simple, straightforward relationship. That's not what we're covering today. Today we're covering the multi-body problem. And that's going to be tough for some of you. But for others of you, you're going to really wonder why anybody else is having trouble with it. And I can't tell who's who yet, but I'll be honest with you. The multi-body problem is not really any changes. It just adds what happens when two objects interact. So everything we've talked about so far applies. But now we're going to talk about the situation in which Newton's third law also applies. That's the primary discussion for today, Newton's third law. There is a clear colloquial expression for Newton's third law, and I know you've all heard it, so let's start with that. The colloquial is, for every action, there's an equal and opposite reaction. You've heard it? Everybody's heard it. That's not really Newton's third law, but it is good enough to give you the idea of what's happening. The problem is it misses a very specific point that's important. So I'm going to give you the definition I want you to know, but understand the equation for Newton's third law probably does not tell you enough about what it's about, but it's really a perfect representation of what it says. That's the equation. Now, the definition, I'm going to say it. I'm not going to write it because I don't want to. But here we go. Are you ready? I'll say it 3 times, nice and slow. For every force, there is an equal but opposite reactive force. For every force, there is an equal but opposite reactive force. For every force, there's an equal and opposite reactive force. Next sentence. These forces act on separate objects. That's critical. These forces act on separate objects. That's why this equation is so important. And you may want to put some notations about what this is about in your notes, why I wrote it just like this. This says the force from object 1 on object 2 has to equal the force on object 2 from object 1. The force from object 1 on object 2 is equal and opposite to the force on object 2 from object 1. That's what that says. Now, we won't write it out like that generally. We will simply look for the forces that comprise what I like to call action-reaction pairs. That's what we will look for, the action-reaction pairs. Now, this third law of force has been in every problem we've done already this year. They're not hiding. It's just that we've only dealt with one object. We've never dealt with the other object at the same time that is experiencing the Newton's third law of force. So let's talk about a problem that we did do in class. Oops, not that problem. So how about a box on a table? And let's give the table some legs. All right, let's say that you are pulling on the box to the right. And I mean that. You are pulling on the box to the right. Applying some force on the box. Now, without a doubt, everybody in this room can probably come up with the forces that are acting on the box. Let's assume the box is sliding, but sliding or not, you can probably come up with the forces that are likely acting on the box. For example, there's probably not a person in the room who doesn't realize there is mg acting on the box. And it's touching the table, so there's normal force acting on the box. There's U pulling on the box. There's likely friction acting on the box. Now, for every one of these forces, there is an equal but opposite reactive force acting on something else somewhere in the universe. The easiest one to see right here is that if the box is resting on the table pushes up on the box, and the box is pushing down on the table. That is a Newton's third law pair. There's an upward force from the table on the box, and an equal but opposite force on the table from the box. They form a Newton's third law pair. The forces are equal. They're in opposite directions. However, welcome to go if you have your senior shirt on, seniors. These act on separate objects. So when we talk about these forces, it's important you understand the third law of force can't cancel out like people think it does. Like if I push on the table and the table pushes back on me, how does the table ever go anywhere? Don't those forces cancel out? No. The force I apply to the table acts on the table. The force the table applies on me acts on me. I have a lot more friction between me and the ground. Table's on wheels. So the force I apply to the table easily moves the table. But the reactive force on me doesn't move me. There's enough friction to keep me attached to the ground. So when we deal with these forces, we have to realize that they act in pairs, but on separate objects. There's a frictional force acting on the table. Has to be. The table is providing a normal force, so the table is experiencing a frictional force in this direction. That frictional force could force the table to move to the side, unless it's attached to the ground in some way. But there's clearly an equal and opposite force on the table from friction. There's an equal and opposite force on you. Right? You are pulling on the box, so the box must be pulling on you. I don't know if I like that. Force must be pulling on you. Yeah, better, I think. I don't know. I mean, it was coming off its belly button, so we don't make it dirty. But yeah. We'll just stop talking right there, Mr. Shelton. Leave it in the video, though. It'll be fun. All right. Now, we've covered almost all the four forces there, but remember, every force has an equal but opposite reactive force. So, you zoom that sucker out, you understand that there is a great big world here causing gravity. So, although there's a downward force on the box from the earth, there's an upward force on the earth from the box. It's the same size force. They are the action-reaction pair. But we don't worry about the box somehow causing the earth to move. And although it's easy to trick you on multiple choice, the effectiveness of a force depends on the mass upon which it acts. So yes, there is a force upwards on the earth from the box, but the earth is really, 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 really big. You know, like 6 times 10 to the 24 kilograms big. Is there going to be a whole lot of acceleration from that weight of that book? Very unlikely. Moreover, keep in mind, this third law of force is happening everywhere in the universe. You drive down the interstate, bug hits your windshield. Who experienced the bigger force, you or the bug? No, you experience the same size force. See, I did it to you already. You got it wrong on the first try. Newton's third law says you experience the same force as the bug. Which one is more affected by that force? The bug. That's right. The bug is small. So when it experiences that force, it blows it apart. When you experience that force, you're mad because your windshield's a little dirty. Right? But still, that's the way it works. They experience the same size force. So you're driving your smart car and it gets hit by a semi. Which one experiences more force? Neither. They experience the same force. twice, right? Did I catch somebody twice? Really? Because I don't want to be in the smart car if it gets hit by the semi. Because it's going to be more affected by that force. It's small. The semi will just drive right through it. Right? It might not even slow down very much. But the smart car might change direction. Right? That's the idea here. The forces come in pairs. They must be equal but opposite. There is no exception here. So any of your what ifs are garbage. For every force, there's an equal and opposite force. And this is the best part. They all happen at the point of contact, except for the fundamental forces. They all happen at the point of contact. So you can see it. It's that straightforward. I rest my hand on the table, which means I'm pushing down on the table. Table's pushing up on my hand. It's happening right where the point of contact is. You don't have to guess about these forces. They occur, every normal force, every tension force, every friction force has a third law component. All of them. All right, that's force. I said that a lot. Doesn't seem to matter though. I can easily fool you. So when I say that, I mean, look, there's some simple examples that no matter what I say, seem to fool people when I ask them the question. So imagine, I'm going to have to draw a car again. Let's make it a Volkswagen. There. Oh, it's terrible. But that's your car. So that's our car. Let's make it not a floating car, but a car on the road. There we go. All right, and our car is going this way. And there is a bug right there. Okay? Bug strikes the windshield. You've all experienced this, or at least seen it done. What experienced more force, the car or the bug? Actively trying to trick you, and it's not a trick. Newton's third law makes it clear. The car pushes on the bug. The bug pushes on the car. Does that sound like an action-reaction pair? If it is, and it has to be, anytime there's a point of contact, that's the action-reaction pair. For every force, the point of contact is where the action-reaction pair occurs. The only time that doesn't work is for something like gravity, where they don't have to be in contact to experience that force. That's why gravity is weird. Every other force requires contact. So in the case of this problem, the bug strikes the windshield, which means the bug experiences a force from the car. And the car experiences an equal force from the bug. So why does the bug splat and the car doesn't? Just because they experience the same force doesn't mean that force is effective. That force is very effective at changing the velocity of the bug. Is it as effective as changing the velocity of the car? No. Even though they experience the same force, that unbalanced force acts on two different things. So there would be the Newton's second law that acts on the bug, and the Newton's second law that acts on the car. Now I'm drawing it like that to exaggerate something here. The bug has a teeny tiny mass. So that force is very effective at causing the bug to accelerate. But the car has a massive mass compared to the bug. Therefore, that force is not nearly as successful, but these both have to equal the same force. A Newton's third law force. So if you're driving your car and it gets hit by a semi, which car experiences more force, your car or the semi? They experience the same force. It's just way more effective at changing the velocity of your car than it will be of changing the velocity of the semi. But they still experience the same force. So if you get hit by a boxer, it might be more effective at knocking you out because his hand is what experienced the force. But your face might be the thing that experienced the force from his hand. That could make it more effective at changing the acceleration, changing the velocity of your head. It might be less effective at changing the velocity of his fist. When you watch boxing, that's what they're trying to do. So when we deal with Newton's third law, the law acts on different objects. The effectiveness of that force depends on the mass of that object. You'll hear me say that a lot. The effectiveness of that force will depend on the mass of that object. So even though it's the same size force, doesn't mean it's as effective on both objects. Effectiveness is important here. Look, if I push on the table here, the table's going to move. I experienced the same force as the table. Why didn't I move? Well, probably because I weigh a lot more than the table does. But it's more than that. The table's on wheels. When I apply the force to the table, although it experiences a force from me, that same force is experienced by me. I don't get pushed backwards because I have shoes on. And my shoes have a coefficient of friction against the ground and are not going to roll. So I don't go flying backwards because I pushed on the table. But I do experience an equal and opposite force that the table experiences. Why does the table move? Because that force is more effective. It depends on what's happening to the table. It's on wheels, less friction, it probably rolls. If I go and push on the table over here, the opposite will happen. It will never move and I will be pushed backwards. Why? Because the table is screwed in place. It's mounted to the floor. Unless I can push hard enough to break the mountings off the floor, I am likely going to be pushed backwards. Who experiences more force? Neither. I experience the same force as the table. It's just more effective at moving me backwards than it will be at moving the table. I want to see how this works out. And so in practice, we're going to look at 3 different examples. The first example that I want to do in here are train problems. I picked these first because they are largely a direct result of what we just described, but they're the least interesting problem. They're the most likely to show up on the exam combined with something else. They will usually not be on the exam on their own. There's 2 versions of this problem, and so I want to show you both versions, but they are effectively the same problem. There's 2 or more objects in a row that are in contact with each other. Something like this, where there's a force applied, say, to this box. Okay, so we have, say, box 1 and box 2. Very similar question is to take those same 2 boxes, but this time, instead of have them in contact with each other, have them separate, but connected by, say, a cable. Again, box 1, box 2. These are the same problem. No matter how you look at them, they're the same problem. The only difference is that contact between these 2 is through a normal force, because both surfaces are in contact together, and contact between these 2 is through tension. But they're arguably the same problem. What I want to do is I want to talk about these problems, and I want to talk about them for right now with no friction, just so you get an idea for how to deal with these kinds of connected problems. And it doesn't matter whether there's 2 objects connected together or 100, it's all done the same way. There are shortcuts here, and you should see the shortcuts. I'm going to try and show you the shortcut at the same time as I'm showing you the long way around. You'll need to be able to do both. Everybody ready to go? All right. I'm going to skip talking about the forces that are in the y direction for these 2 examples, because the y direction would produce up and down weight and normal force on all 4 of these boxes. Do you guys agree with that? Those forces will likely sum to be 0. Do you also agree with that? So if there's no incline, that seems like a pretty easy way to go. Good? Now if there's friction, can't do it that way. If there's friction, I'm going to need the normal force because friction is equal to some proportion of the normal force. But if there's no friction, I can ignore that and just deal with the horizontal forces. So in the interest of time, I want to consider the horizontal forces acting on each of the objects, and we're going to look at both problems simultaneously, just so you can see that they're the same. So first, let's start out with the force on the M1 box, and we'll Let's just divide this in half real quick so we can understand we're dealing with two different problems, but they're very, very similar. All right, so the M1 box is definitely experiencing a force to the right. Right, that blue box? In fact, maybe it'd be better if I just went ahead and made that blue so that we can clearly see which is which. Now, it's in contact with the M2 box, so there must be a normal force this way. It's a surface. It is a normal force. I did not put a subscript here, but you know that means the blue box is experiencing two different normal forces, right? It's got another normal force in this direction, but that's purposely why I was leaving out the vertical stuff, to not confuse us. So there, you can have a situation in which a box experiences more than one normal force. That shouldn't be a surprise. Any surface in which it's in contact will apply a normal force to the box. And the force on this box has to be to the left. That also shouldn't be a surprise. It has to be a left because it has to be perpendicular to the surface in contact, and therefore it must push the M1 box to the left. At the same time, the M2 box is experiencing a force. The force it is experiencing must be a normal force to the right. And this normal force and this normal force should be drawn in such a way as they are equal. They represent the Newton's third law pair. The biggest mistake made by students is they somehow believe this force is acting on this box, and it is not. That force is only acting on the blue box. The red box experiences a force from the blue box, from the fact that the blue box is being pushed into it. But that's how the force gets expressed, by going through the blue box to get to the red box. Now, this same kind of argument can be applied to the other situation, except that in the other situation, I kind of have to start with I don't have to start with the red box, but I'm going to start with the red box because that's where the applied force is. There's a force here, a tension force. I labeled it F, so I'm going to stick with F. But the red box is also experiencing a tension force this way, because there is a string connected to it here. Now, this statement is a statement I've made before, but I'm going to reiterate it. In a string, the tension is the same everywhere in the string. That's more or less true first semester. It's going to stop being true second semester, but it's true first semester. I'm saying that because the blue box must be experiencing a equal and opposite force this direction. The tension acts to pull the blue box to the right. And these two forces must constitute, these two forces must constitute a Newton's third law pair. They are equal but opposite forces that exist through the contact point between the two boxes, the string. Now, what happens next is pretty straightforward. First, do you notice all I've done so far is my set of steps for drawing my free body diagram? I'm going to ask myself if I think this is a first law problem or a second law problem. What do you all think?
First law?
If there's no friction, I think this is a second law problem. They look unbalanced. There and there. Would you agree? So I think it's a second law problem. Moreover, without friction, it'd have to be a second law problem. There's more to it, though. In a problem that has more than one object, the way I would like you to solve them, and this is probably the most important thing I'm going to say today, most of the stuff is reiterated from last week or weeks ago, this part's important. Choose a common direction for positive. This is different than how your book does it. Choose a common direction for positive. Semicolon. Make the positive direction the direction of the acceleration. For a connected problem, if that fails, choose the direction of the velocity. For a connected problem, if that fails, if there is no acceleration or you don't know if there's an acceleration, make it the direction of the velocity. You will be happier if you do. I have a very clear direction and I think the system is going to accelerate, so I think we both know that this is going to be the positive direction. I'm going to continue to do the set of steps. There's nothing extra now. Each object is evaluated by using Newton's second law. So, net force equals ma. That's where I'm going to begin. I'm going to start with box 1, the blue box on the left side. It's experiencing two forces. It's experiencing F to the right, N to the left, and that has to equal M1A. Move on to the red box. It's experiencing one force. It's the only force acting horizontally. That has to equal M2A. I've applied my set of steps, and my set of steps has given me two relationships that may or may not be able to be used to figure out what our problem is about. You should be able to do the same thing on the other side. It's not hard. Do it real quick. What are the two relationships you're going to come up with on the other side? So on the other side, you should have T equals M1A and F minus T equals M2A. Pretty easy, pretty straightforward. Now, it's what happens next that matters. Newton's laws can only generate for you a relationship. It's what you do with that relationship that matters. And that's going to depend on what the question's going to be. There's some obvious questions here. Like, what's the acceleration of the system? What's the tension in the cable? What's the normal force between the boxes? How long does it take until the system gets to X velocity or something like that? So you may or may not know what to do next, but usually it's going to involve finding something out about the system. The most common question would be find the acceleration of the system. And that should be pretty straightforward. If you don't see how to do it right now, you see substitution, right? I can eliminate the normal force between here. I would encourage you to learn some things to do here, some ways to do this that aren't just about substitution. I'm providing you with not a trick, but a method. By doing this, by setting the common direction to be positive across your problem, you should always end up with a situation in which one of your internal forces is negative and one of your internal forces is positive. The normal force is considered internal to the system of masses. And they should act in opposite directions from each other, so one should end up being positive while the other one ends up being negative. This gives you a real simple way to eliminate variables. This is especially true if there's more than two and you have 3 or 4 or 5. This becomes a lifesaver on speeding up substitution. What I'm asking you to do is just add the two equations together. Bank the equal signs and add them together. I get M1 plus M2 times A on the right side and just F on the left side. This works regardless of the method or regardless of what's connecting your objects together. Right? That happens over here too. So over here, I get F equals M1 plus M2A. Now, one hint. This is something you might want to write to the side. It's a hint. in these problems, you will often come to this point where you have eliminated the internal forces. That's very common. We have done so. When you get to this point, you should see a system-wide equation. You should see it clearly. That's what I have here. I have a system-wide equation right here. I have the external force acting on the system, somebody pushing on box number 1. I have the mass of the entire system here and the acceleration experienced by both objects. When you reach this point in the problem, you should see a clear system. Same over here. In fact, you'll notice that if the two systems were the same force acting on both, they'd experience the same acceleration. That's not a surprise. The train question is pretty straightforward. There's not a lot here, but you probably can understand that you start adding friction to this problem. You start putting the whole thing on an incline, and you can start to see the problem develop, right? Friction is going to make the problem more interesting automatically because that means that there will be something added here for every one of these objects. Putting it on an incline adds even more. Follow along? We're going to do more complicated problems today, but I'm trying to just introduce. Any questions about these two examples, about what it looks like, how to get them set up and started? You understand that once you find the acceleration here, you can go back and find out what that force is between the boxes. That would be the very first thing I would ask you guys to do. And so I have the same way of doing it here and here. Find the tension. There's probably a couple of you guys who are pretty shrewd and can see something bigger happening here too. And if that's you, great, use it to your advantage. If it's not you, let me draw your attention to it. So, if you're paying attention, from the outside world, how is the problem we just did very different from a single box of mass m1 plus m2 experiencing a force to the right, like so? The applied force doesn't know that there's two boxes there. The applied force doesn't know anything. The effectiveness of this force depends on the inertia of the system. If I didn't know there was a couple boxes here, if I just knew that the system had a combined total mass of m1 plus m2, it'd be as if this was just one big box, right? That's what we got at the end anyways. Our final relationships at the end were as if we had just one big box of M1 and M2. If there's no friction or any other complicating procedure in your problem, you could probably just make the assumption that this is what you have to figure out the acceleration without doing all the complicated stuff we just did. It doesn't work every time, but it works really frequently. And some of you probably can see that, why wouldn't it? I say this because this would be really tedious if it was 10 boxes in a row, wouldn't it? Because you'd have 10 different free body diagrams, 10 different sets of force equations, 9 different tensions between the boxes, or 9 different normal forces, when you could treat it like one box with the mass of the 10 objects in it. It's a good shortcut for problems that are really big, especially if that really big is designed to test the tediousness of the problem. So you can jump to this. There's no reason why you can't think of this as a system. Net force equals mass of the system times the acceleration. You'll still have to do stuff to find the internal force, sure. You're not going to get away from that, but it does save an incredible amount of time to start knowing this has to be the acceleration of the system, right? It saves you an incredible amount of time. And to be honest, this would be true even if there was friction and even if the whole thing was on an incline. You can almost always set it equal to a single box that has the combined mass of both. The only time you can't, and I would put this in your notes, the only time you can't is if the coefficient of friction is different for each box. Then you wouldn't be able to do it. But if it's not, you can treat it like one box, one coefficient of friction, one angle, the whole bit. That works to get you what the acceleration is. Saves you a ton of time. All right. Second. Now, I'm going to draw this out. It'll take me a minute. It is worth you guys drawing some of these pictures. So I'm going to just talk about the names because the names are going to be all over the test. All right, these are all called Atwood machine problems. Every one of them is called an Atwood machine problem. So whether we have an object on a table with something hanging off the edge, that's one kind of, this is called a modified Atwood machine. This is a modified Atwood machine. This is just known as an Atwood machine. The Atwood machine problem is one of the more common problems on an AP Physics exam. It shows up all the time in the research, shows up all the time in the literature, it shows up all the time on the exams. Every single book is going to have dozens of questions about the Atwood machine, and there are so many Atwood machine questions, it's almost crazy. So let me just start from the beginning and say the Atwood machine problem is one you have to nail. It's going to be on every problem. You're going to have a ton of practice on it. Of the problems I'm going to hand you, a lot of them are going to be Atwood machine questions. For the time being, an Atwood machine problem features a pulley somewhere in the problem. Generally, there's 2 or more weights. I say 2 or more because it's not uncommon for an actual Atwood machine question to have more than one weight associated with it, like something like this. So 2 weights on one side, 1 on the other. It's really, really common. An Atwood machine question like this, where you've got an incline, obviously that means they can test 2 things at once, your ability to do inclined plane problems and your ability to do multi-body problems. So you can understand that this is really where they're going to spend their time. This brings all the pieces together. And so these are pretty typical. We're going to start with the modified Atwood machine, this one, and do some examples on what I expect you guys to be able to do with the modified Atwood machine problem. However, all Atwood machine questions that we do this year all of a sudden get more complicated next semester. For right now, in our Atwood machine questions, in any cable in the system, the tension is the same everywhere in the cable. That makes a big difference next semester where that's not true. It's true now because we're going to say that our pulleys are massless. They have no inertia. As long as that statement is being said, then the tension on the pulley has to be the same on both sides. What that means is there's a tension this way on that red mass, but there's also a tension this way on the pulley. That's the actual Newton's third law pair. But there's also a tension this way on the blue mass and a tension this way on the pulley from the blue mass. That's a Newton's third law pair. As long as the pulley is massless, this tension and this tension are the same. As long as the pulley is massless, those two tensions have to be the same. The moment the pulley has mass, those two tensions are not the same. So first semester, we can say that the strings have the same tension everywhere. That's why I brought it up earlier, why I'm bringing it up now. I'm telling you when that's not true. You have to listen for that in the problem. So if they say to you that the pulley has mass or the pulley has inertia, you will not be able to let those two tensions be the same. So first semester, they will be. Second semester, no, they won't. So first example, we're going to do a modified Atwood machine question. And I know that I'm doing, M1 and M2s and stuff like that today. This is really just about getting you guys to set these problems up. I know you would probably prefer to have numbers, but you and I both know that it's more likely that you're going to have problems that are just going to be relationships. So M1 on the table, M2 off the table, and we'll say still frictionless problem. Okay. So we're going to launch into this one, but I want to give you a kind of an overview. Atwood machine questions are about understanding inertia. That's really what they're about. They're designed for you to understand or to be testing yourself on your knowledge of inertia. That's what their whole thing is about. So we're going to start the problems kind of the same way we've been starting them. Do we think this is going to be a first law problem or a second law problem? It's going to be a second law problem. I think the system's going to accelerate. Do you guys agree? Now, we're getting into the idea of pulleys. So we're gonna add a little bit here. You should ask yourself if the motion of one object is related to the motion of another. In the ones where it was a train or something, that was pretty easy. These are going to start getting more complex. So does the motion of one object, is it connected to the motion of another? What we're looking for is, if we think that both of these are accelerating, are they both accelerating the same? Now, I'm being careful because there are ways to set up pulleys where that won't be true, where the motion of one object can be a different proportion than the motion of the other object. So ask yourself something stupid simple. If this object moved 1 meter this way, would this object move 1 meter in a similar direction? Understand whether there is a one-to-one correspondence in their motion. There doesn't have to be. And I'll show you situations in which there's not. For right now, though, this situation's pretty easy. Unless the string stretches, if this one moves a meter, this one's going to move a meter. Agreed? Okay, so ask that question. Is there a relationship between the motion of the two objects? Check for one. If so, great. Label a common direction positive. Now, these problems are very similar. You should be able to set this problem up pretty easily. Free body diagram for the object on the table. I think it's experiencing three forces, don't you? It's going to be experiencing tension to the right, weight downwards, normal force upwards. Box on the table. What do you think? You can do this one. You don't need my help. Start to be careful, though. it's at this moment that you guys should start really being more careful about how you draw your forces. The only way this box accelerates downwards is if the weight downwards is larger than the tension upwards. But the tension here and the tension here have to be the same length too. You should start being considerate if you're drawing the length of your arrows proportional and correctly. On your test, for me to prove this, I put the free body diagram in a box that has gridded paper inside of it so that you have clear ways of comparing the length of the vectors you draw. You should expect to see that on your next test. And your grade will be based on whether you draw the size of the arrows proportionate to an appropriate scale. So I would argue that I probably should shorten the tension here up to make it more obvious that the downward weight is greater than the tension, and be similarly consistent on this side to make the length of this tension similar to the length of the other tension. That length versus that length. Now the actual math here, not hard. I've got tension equals M1G here. I'm sorry, M1A here. Pretty straightforward. There's only one unbalanced force, that's the tension, and therefore my object's acceleration is based on that. On the other side though, I have M2G minus tension equals M2A. You'll notice I made weight downwards positive. That's because I'm being consistent with my direction here. By drawing my direction clockwise along the pulley, I'm saying this way is positive with respect to this mass, and this way is positive with respect to this mass to keep the acceleration a consistent direction. Again, I said, make your accelerations consistent. That's it. That's all Newton's laws can do. So in this problem, we've done all the Newton's law portion. There's probably more to do. Looks like I could eliminate tension here, get a relationship for how fast the system accelerates. This also will not be a surprise. If I wanted to find out about the acceleration of the system, I just add these things together. Left side I get M2G. Right side I get M1 plus M2 times A. This isn't a surprise, but students mess this up all the time. The unbalanced force is just the weight that we hung off the edge of the ramp, or off the edge of the table. And I still get the sum of the masses in here. I said to you before, when you eliminate the internal force, you should get something that shows you the system's acceleration based on the mass of the entire system. If you don't add up all the masses someplace in the problem, you've made a mistake. You should always see that happen. If you've been paying attention, you should have no difficulty doing this example. Everything you need is already there in your work. I'm going to throw in some numbers here for funsies. All right, here's what I want. I want the acceleration of the system. I want the tension in the cable. And I want the upward force on the pulley. You may still assume the pulley is massless. Look, I don't want you guys to not have an understanding of what you should have been expected. T up for both, the same. This one has to be longer, 450. This one has to be shorter than T, 350. I'm exaggerating it a lot to make sure we understand that the upward force of tension is the same on both sides, but in order for it to accelerate this way, this arrow has to be longer than this arrow. And this arrow has to be shorter than this arrow. This way is positive on this side, this way is positive on this side. All good? Because if you don't understand that, you need to ask. All right, so T minus 350 equals 35A. Net force equals MA. 450 minus T equals 45A. Net force equals MA. Any questions? What?
If you're accelerating, going like this way, clockwise, why would it be T minus MA and not, or T minus MG and not MG minus T?
Because upwards is positive on this side, and downwards is positive on this side. So, folks, if you take this over here, add them together, you get 80A on this side, the total mass of the system. The T's cancel and you get 450 minus 350, which is 100 on this side. So the acceleration is 10/8, 5 force, or 1.25, right? Meters per second squared. Questions? It's a lot. Practice. Your homework will be posted probably around 4:30. Doesn't matter which one of these you choose, but you can take this acceleration and plug it into any one of the any one of the functions. So I would plug it in, say right here, and you can solve T from there. Does that make sense? So like, let me just grab that one. I'll get 450 minus T, yep, equals 45 times 1.25.
And the upward force, like,
The pulley is experiencing tensions down, 2 of them. So some upward force from the ceiling has to be balanced.
so it have to be the same
So that's how you get that.
from the two atoms together.
Third law.